This is it? This is really all that's showing up today, huh? Okay. Fill that in. Well, how about, so how's the homework coming in? Do y'all have any questions on the homework assignments? Do any of you have homework ready to turn in?
I do.
Well, I guess we will keep going where we left off. We were talking about solving problems using the conservation of mechanical energy. We did the falling rock and the roller coaster. Turn in your book to page 153. The picture there, figure 619, showing the two people on the two different water slides. And they both start off at the same height. And they both start off at the same time. And then they ask which rider is sliding faster when they get to the bottom. And they ask which one gets to the bottom first. So let's talk about the first question, the first part of the question first. When they get to the bottom of the water slide, you see one of them starts off very slowly and then drops abruptly. Whereas the other one starts off faster, levels out, and then drops down to the bottom. So the second one, ready to jump? Second one starts off going faster, accelerates a little faster at first. Let's see. Here you go. And but do you see how it doesn't matter how they accelerate and which one accelerates faster first? That at the bottom, they are both going to be going at exactly the same speed. Do you understand how and why that would be?
Since they start at the same height, they have the same amount of potential energy.
Exactly. That's the whole point, at least of the first part of this. That's exactly the whole point. They start off with the same exact energy, total energy. They both start off with the same potential energy, and if they both start from rest, they start off with the same kinetic energy, which means they both start off with the same total energy, They're both going to have the same total energy at the bottom. They're both going to be going just as fast. Now, second part of this question may not be quite so intuitively obvious. It asks, which one gets to the bottom first? And also, we're going to ignore friction, obviously. They're on a water slide, so we're going to assume it's frictionless. What do you think? Which one gets to the bottom first? No, not really. You can. How can we put this so it makes intuitive sense? He spends all of this time going slower than she does. Right? They both start off at the same instant. So from here to here, he's going a lot slower than she is. She's already sped up and has gone way down. Okay? He is going to accelerate exactly the same amount that she accelerates. So by the time he gets to the bottom, he will be going just as fast as she is. But because she accelerates faster first, he's never going to accelerate fast enough to catch up to her. She slows down a little bit here, but you can kind of intuit from the shape of the graph that she's not going to slow down as much as he does right up here. And so it's like the old, how many of you have ever been pulled over by a cop for speeding? You ever been pulled over for speeding? You've never been pulled? How? Are you a cop? No. Okay. You ever been pulled over for speeding?
Yeah.
What about you, Jim?
Oh, yeah.
Yeah. How does this conversation go? Where's the FAR? We'll just skip past all of you in a whole heap of trouble, boy. We're going to cut right straight to the whole why you should get out of it. I was trying to get to work and I'm late getting to work. If I don't get there on time, I'll get in trouble and I might lose my job. What is the cop's standard canned response? Oh, no, this is yours.
Oh, really?
Yeah, we can keep that.
Yeah, but the exam is over here, so I'm gonna. So I have to meet with the exam, or I'm gonna take it.
No, that's yours. Yeah. Yeah, it's graded. It's yours back. You can throw it away if you want, but
No, I don't.
okay. What's the standard response the cop tells you when you tell him you're in a hurry because you got to get there before it's too late? You never had this encounter, huh?
No.
The standard response, he tells you, well, if you needed to get there sooner, you should have left earlier. Okay, and it's true that you can't make up lost time. Point is, unless she slows down enough here for him to catch her, he's never going to make up that lost time. So she will get to the bottom before he does. She gets there first because she started first. You know, have you ever been in a drag race? If you leave the line first, the other person's going to have a hard time catching. And yeah, obviously you've never been pulled over for speeding. Never been drag racing, I take it. No?
Well, I have been in a drag car before.
Oh, really? Did you seriously? You drive? Drive racing? Drag
I
racing?
didn't drive with my shirt.
Oh, okay. Kind of exhilarating. Well, that's the whole point here, is that they're both going to accelerate the same amount by the same gravity. But the one that accelerates first, they're getting ahead that whole time, and the other person's, it's not like gravity is going to pull that second person faster and harder to try and make up the lost time. No. Point here is to think about these problems, this whole work energy approach. Think about it analytically, but think about it deliberately. And don't start running off on intuitive guesses when you're dealing with problems. It really is a very powerful way of solving a lot of problems. But right here, if you don't really think it all the way through, you can get in trouble. Looking at other forms of energy and energy transformations, the law of conservation of energy. How many of you have heard that said before? Energy can neither be created nor destroyed. It can only be converted. It can be stored or it can be transferred. But it can't be, you can't create new energy, and you can't destroy energy that exists. Let's think about that. What does that mean? What's the difference between physics and chemistry? No, this isn't a rhetorical question. Somebody answer. What's the difference between, how do you imagine the difference between physics and chemistry? If you were trying to describe to someone the difference, go ahead.
Maybe chemistry reactions and the transformation of many
Okay.
the physics just like movement.
Okay. What about you? How would you describe it?
Yeah, we can describe it as like actual person function.
Different kind of energy. That's an interesting way to start thinking about it. What about you?
Wow, I've never had chemistry.
Okay. Well,
I just know it's hard.
you know what?
I know it's hard, so.
Well, yeah, I took 2 chemistry courses in undergraduate school and said, that's it. I'm going to stick to something easier. Chemists and physicists have completely different ways of looking at things. What about biology? How would you describe the difference between physics and biology? Exactly. That's literally the meaning of the word biology, study of life. But isn't that kind of chemistry? I get it. I understand. It's biology is the study of life, and that's how biologists think of things. They perceive things through that filter. Chemists, they perceive their discipline through the filter of they are studying chemicals and chemical reactions. Okay? They are studying the chemical forces involved in those reactions, as opposed to the mechanical forces of moving a box along the floor or lifting an elevator up a shaft. But to a physicist, there's no difference. It's all the same. It's, you talk about different kinds of energy, and that's something that physicists still struggle with. It's different kinds of energy. You notice in here we're talking about this is translational mechanical energy as opposed to what other kind? As opposed to rotational mechanical energy, which, well, that's something different. We have to use different math to talk about rotational energy. But it's all the transfer of energy, the storage of energy. When you're studying electricity, electronics, electrical power grids, it's the transfer of energy. You're storing energy or you're transferring energy, and you're trying to do it as efficiently as possible. If you're designing a circuit board or writing a program to control a microprocessor or a PLC, you're storing and transferring energy to accomplish something or to describe something. Chemists look at how chemicals interact, and they call it a chemical force, as opposed to nuclear physicists who deal with nuclear forces. But it's all just energy. It's the transfer, the storage, the conversion of energy, friction, non-conservative forces. Is that destroying energy? No. It's converting it and making it unusable. Because once it turns to heat, that's it. It's gone. Once energy has been reduced to that ground state of raw heat, it's pretty much over. Now you can generate heat to store energy in, say, a mass of water by turning it into steam, which produces pressure, which can then be converted into mechanical energy, or that mechanical energy can turn a giant armature inside a generator to produce electrical energy that can then be transferred somewhere, that it can be piped through the element on a stovetop and turned back into heat so it can boil water to cook a meal. But it's all just the transfer, the storage, or the conversion of energy from one form to another, as he called different types of energy. And this is a question that raised a point that is I don't know if it's intuitive or insightful, but it's kind of incredible, because that's really a real problem for physicists, science in general. What is energy? And at the end of the day, we're still having a hard time wrapping our mind around defining exactly what energy is. It's kind of like the Supreme Court Justice said about pornography. He said, I can't tell you what it is, but I know it when I see it. Well, energy is that way. We know what it is. And we have statements about it that are true. It's the ability to do work. Okay? But at the end of the day, the universe, the entire universe, contains a fixed amount of energy. Most of it is, or I say most of it, I don't know, I haven't done an astrophysics, haven't really looked into it, but a huge amount of that energy is stored as matter. What's the most famous equation in all of science, in all of the world? If you're looking to write an equation on the blackboard that looks sciencey, what's the first equation that comes to your mind? Bingo. E equals mc squared. What does that mean? Mathematics is a language. We use it to describe the world we live in, the world we observe. What does that equation actually mean? What's your guess, Jeff? What do the letters stand for? Do you know that? That's correct. What's the E stand for? Not voltage. Energy. That leaves M. What does the M stand for? Bingo. Mass. What is mass? It's a measure of matter. Exactly. Measure of matter. What about this? Speed of light. What is that? And why on earth did he use the letter C to represent the speed of light? Have you ever thought about that? Why? Why did he pick C? Is that like the German word for light? Maybe it was. Just guess. Why might he have used the letter C? And I'll tell you now, it's not because he was French and thought it should be candela or some French word for light. So the formula would sound cool. That's as good a reason as any, I guess. No? Got a guess? Any guess? Pick a guess, any guess. What was Einstein struggling with at this point? I know y'all probably aren't familiar with the history of what went on back at the end of the 19th century, but have you ever heard of the UV catastrophe? Some of the models of the atom, they were coming up, we had figured out that atoms existed. The existence of the atom was first postulated in like 400 and something BC by an ancient Greek philosopher named Democritus. And that's where we get the word atom, because he postulated that for all of the things that the world is made up of, for all of the elements, the dirt, tree, leaves, grass, air, water, fire, all of those philosophical elements that there were countless of. Blood, meat, hair, dirt. These were all the elements that the world was made up of. And surely, he said, there must be a point where there is you cut it in half. You take a piece of rock and you cut it in half and you have two smaller pieces of rock, like magnets. Take a magnet, break it in two, you've got two magnets. He postulated that if you cut it down, you keep cutting it to smaller and smaller pieces, at some point you're going to get down to a fundamental piece of that element that is so small that if you cut it again, it will no longer be whatever it is. It'll be whatever it's made out of, but it will no longer be that element. And because he was an ancient Greek and spoke Greek, he used the Greek words for not cuttable. Mos, or atom. That's where we get the word atom. It's the ancient Greek for not cuttable. Well, he had postulated this, but that was about as far as it went. For a couple thousand years, then some, I think it was Russian scientists figured out that when they started identifying certain elements that really were not cuttable, that were the smallest elements that everything was made out of, you noticed that there was a periodicity of the way they started coming together, and it was, there was very discrete steps between them in terms of the mass, and came up with the periodic table of the elements. Not long after that, we finally figured out that, hey, look, the world is not made up of millions and millions of elements. It's made up of about 100 of them. And everything else is just different combinations of those 100 elements. And that then brought up the question, well, what are the elements made of? And they started studying about atoms, how atoms are built. They came up with they came up with all kinds of different models of the atom. What would an atom look like? What is it made out of? And they figured out, well, it's made out of electrons and protons, and there are these neutrons in there. One of the early models of the atom was it's like a big old ball of cookie dough, of positive cookie dough. And that was the protons with some neutrons added in. And then the electrons, which were the negative charges, would be added into the cookie dough like chocolate chips into the cookie. And then Niels Bohr figured out, well, no, the atom is mostly empty space. And that just really blew people's minds. I don't want to turn this into a history of the development of modern science, but when Einstein was on the thing, came on the scene, the big problem was this whole speed of light. It was messing everything up. It turns out that it didn't matter how you measured it. It didn't matter what reference frame you were in when you measured it. It defied everything we understood about the relative motion, the Galilean relativity. If you're moving, if the train is moving at 80 miles an hour and you're throwing the ball on the train, then the person on the ground sees the ball moving at however fast you threw it, plus the 80 miles an hour that the train's going. Remember all that? Didn't work with light. It was like, well, if light is moving at this speed and you're moving towards it, well, then you should measure it as moving much faster because it's your speed plus its. But that didn't happen. It did not matter at what reference frame you measured light from, it was always the same speed. It turned out to be, 299 million meters per second, something like that. 186,000 miles per second. Very, very, very fast. In fact, until the late 19th century, no one could measure the speed of light. They just lacked the technical capability to do so. Finally, about the end of the 19th century, they got to where they could make some pretty good measurements of the speed of light, and it was just messing everything up because it didn't matter what reference frame you measured it in. It was always the same number. And so Einstein began to develop his now famous theory of relativity on the premise, the hypothesis. What if the speed of light is a universal constant? What if it doesn't matter what frame of reference you measure it in? It always measures the same because it's a universal constant. Had absolutely no idea why or how that might be the case, but he just said this is what all of the every experiment ever done tells us, that as far as we can tell, it's a constant, it's a universal constant. So what if that's true? Then what are the consequences of that? And that's how he developed what he would call, and others after him would call, his theory of relativity. And that's why he used the letter C for the speed of light, because it was a universal constant. Now, in light of, no pun intended, in light of all of that, now let's look at what this equation, this most famous of all equations, actually says. Because energy, whatever that is, whatever energy is, it is equal to the amount of mass you have times this universal constant. So stop thinking of it as the speed of light. It is the speed of light. The speed at which light propagates in the vacuum is this universal constant. But if we take that constant squared times the mass of an object, that gives you the amount of energy stored in that chunk of matter. And it's lots. Lots. When you talk about an atomic weapon, an atom bomb, the kind we dropped on Hiroshima and Nagasaki, you're talking about releasing the equivalent amount of energy of millions of tons, not pounds, tons of TNT. When you hear them talk about nuclear warheads and nuclear weapons, and they talk about the yield in terms of megatons, this is a 50 megaton warhead. That's what that means. It means it will release the same amount of energy as 50 million tons of TNT, trinitrotoluene, dynamite. That's a lot of energy. But that isn't even a fraction. That's only a tiny fraction of the total energy stored in that fissionable material that makes the atom bomb. When you take an atom and you split it in two, you break the two halves of it apart, and so it becomes two smaller atoms. If you start off with 95 mass units in one atom, and you split it apart, what's half of 95? Well, let's say 90, so it's easier. You would think, well, you have 45 mass units here and 45 mass units here, or maybe it's 50 and 40. And to one decimal place, that's true. The difference is going to be out in the second or third decimal place, because this one is not going to be quite 40. It's going to be more like 39.995 mass units. And this one's not quite 50, it's more like 49.995 mass units. So you have like this 0.01 extra mass units that went somewhere. It just disappeared. It didn't just disappear. That's the energy that was released in the explosion. And it was converted to heat and pressure and sound and all of that massive destruction. Think about that for just a minute. The most powerful weapons we have ever built are only using a tiny, tiny fraction of the energy described by this equation. Just imagine what could happen if they ever came up with a way of actually converting matter into pure energy. Well, in fact, there is a way called annihilation, which is a poetically ironic word for it. You've heard of antimatter. Well, antimatter is real, it does exist. There are antiprotons and anti-electrons. In fact, anti-electrons are called positrons. It's exotic matter. You can only produce it in high energy reactions, collisions, but it's real and it can be made. When a positron, a positive electron, and a regular electron, when they meet, they combine, and all of their mass is converted back into pure energy. Same with protons and antiprotons, except that's like 1,800 times the mass of an electron. Fortunately, no one has been able to produce enough of antimatter at one time to produce anything with enough yield to actually weaponize it. And hopefully, no one ever will, because that would be bad. If nuclear weapons are bad, this is, antimatter weapons would be just unfathomably worse. And this all comes out of the fact that energy is conserved. You cannot create it, you cannot destroy it, you can store it, you can convert it, you can use it, but you cannot create or destroy it. There will always be as much energy as there is. There will never be any more. There will never be any less. And according to the laws, not the hypothesis, not the theory, but the law of thermodynamics, it is the inevitable fate of this entire universe, not just this planet, not just this galaxy, the whole universe. It is the inevitable fate of this entire universe that someday all matter will have eventually converted into raw, unusable heat. And that's it. That's all that there will be left. It will be an entire void, an expanse of nothing but raw, unusable heat. That's the second law of thermodynamics, that entropy always increases. The best you can hope for is to stop it from increasing, and then only for a little while under very tightly controlled conditions. That as soon as you stop controlling it, it will start to increase again. And that means energy gets converted into raw heat. But once we understand that energy is conserved, all of a sudden things start getting a lot simpler to deal with, to figure out, to calculate, to understand. And this whole approach of energy conversation, energy conservation, the energy work principle of solving physics problems. So I said it's a very powerful way of approach. It's a very powerful way of looking at things. And it doesn't just apply to moving boxes across the floor or, you know, people riding down water slides. There's more to it than just being able to come up with make roller coasters. Now, energy conversation with dissipated forces. What's that mean? Page 156, 69. Energy conservation with dissipated forces. What does it mean? Isn't it funny how this works? You can read something and you know exactly what every word means, but you have no idea what the sentence says. I did a paper when I was in undergraduate school. I say a paper. I did write a paper, but I did it as a seminar presentation for a course I took this, and I wrote it on the what's called Gödel's proof. He was a guy back in the 1930s, published in the 20s and 30s, published a paper in 1931 called "On Formally Undecidable Propositions of the Principia Mathematica and Related Systems." Only that's not what he called it. He published it in the monthly magazine for mathematics and physics. Only that's not what they called it. They called it Mannschaft für Mathematik und Physik. And he called his paper Über Formal an den Scheidwehrsatz der Principia Mathematica und Verwandte Systeme. Because he was German. And so was the magazine where he published it. And while I could find books written about it, I could not find anywhere the actual paper. But he wrote, well, I could. I got the original copy from my library. I got a print of the original paper from my library. The whole thing was in German. Didn't mean a lick of good. So I got a friend of mine, a girl I knew from college, who was she was a military brat. She grew up. She was born and grew up. She was American, but she was born and grew up in Germany. German was her first language. This was back before the Berlin Wall fell. Anyway, she didn't learn to speak English until her daddy got moved back to the States. She was like 4 or 5. And by then, she'd been speaking German her whole life. She had to learn to speak English. So I got her, I bribed her. I said, look, I'll buy you a fancy dinner and you'll come with me to a restaurant and help me translate this paper. She said, sure. So it cost me a very expensive steak dinner. And she got like 2 sentences in the opening paragraph translated in 4 hours. Because, like I said, she has, I know every word here, but I don't have a clue what he's saying. So, look at this title. Energy Conservation with Dissipative Forces. One word at a time. What does that say? Obviously, we're going to talk about solving problems using energy conservation, but this time with dissipated forces. So what are dissipated forces? What does the word dissipate mean? how you have to approach things like this when, you know, scientists especially, they love to use big words that no one else knows, or that people, not that they don't know, but that they don't use. And so they have to stop and think about, wait, what did you say? Dissipated forces is just a force that dissipates energy. So, it's saying is now we're going to look at solving problems, but we're going to include non-conservative forces. So we're not going to ignore friction. We're going to start considering what about energy that gets spent as friction. Well, this is the whole other half of what's it called? It's called the work energy principle. Not just the conservation of energy. If we could ignore dissipated forces, then there would be if we could ignore non-conservative forces and effects, then hey, let's pack up and go home because we're done, folk. Unfortunately, that's not the way the world works. Energy can be converted. It can be stored. It can be released. But more importantly, it can be converted from one form to another. It can be converted from mechanical to thermal, to heat. It can be converted from mechanical into potential energy and stored in a capacitor, or in a battery, or in a pendulum suspended from a rooftop. This is one I know all about. What is fact? You might want to pay attention, Jeff. This may be as close to chemistry as you ever get. Anyone recognize this? No. Say again? No. Most of them. These are carbons. Which is what makes it organic chemistry. So now you're even one notch higher. Because even people that like chemistry, they hate organic chemistry. That gets weird. These are hydrogens. This is a hydrocarbon chain. We've got carbons with hydrogens bonded on. This would be a saturated fat. And it's saturated because it's got exactly as many hydrogens as it can possibly hold. It loses here, loses two. These bonds will kind of weakly join there. That's an unsaturated fat. More importantly, that's a monounsaturated fat. It means it's lost one pair of hydrogen atoms. Loses another pair, then it's a polyunsaturated fat because it can accept multiple hydrogens. Once it's all full, then it's saturated. Oh, and if it's like this, where it's only lost one hydrogen in a bond, and neither of the neighboring carbons have lost one, then it's got this bond point hanging off of this carbon that's just out there looking for something to latch onto. That's a trans fat. It has nothing to do with its being gender confused. It's just neither saturated nor unsaturated. It's stuck right in the middle and it's looking for somewhere to go. It wants to be one or the other. trans fats supposedly so bad for you, so that they're more reactive. But that's the chemistry of fats. What is fat from a work energy perspective? I told you, for physicists, it's all physics. It's all the transfer of energy. How do you get fat? How do you do it? Eat too much. Eat too much, do too little. What happens? How does it happen? Where does the fat come from? Because, well, I mean, if it's me, it comes in straight on the spoon. Because I eat bacon. I eat real butter. But
I think when we concept the energy,
exactly. This is chemistry and biology and physics all rolled into one big belly laugh. You consume food. You are literally consuming energy. It is no different than putting gasoline in the tank of your car. But like the gasoline you put in the tank of your car, you're not going to burn it all right there. So you have a big tank in the back, or a little tank, depending on what size car you have. And it stores that gasoline as potential energy. Well, your body does the same thing. You eat in 1,500 calories of food, and then you go sit on the sofa and start chomping bonbons and watching Oprah. Your body's not going to just say, well, we don't need this food, so let's just spill it out the other end. It says, well, look, we're not using this food, let's do something with it. And so it converts it. What it doesn't need to burn as energy, what it needs to burn as energy, it converts to sugars, and those get burned in the cells. The rest, it turns into fat. It says, here, go hide out here in your belly, or in your throat, or on the bottom of your arms, or in your backside. And yeah, we could use some more on the backside there, so let's pat that up some more. That seems to be the part we use the most. If you're a woman, it puts them on your thighs. The point is, it doesn't just throw that energy away, it stores it. And that's how it stores it. It stores it as long hydrocarbon chains. And that's what energy does. You convert it, you use it, or you store it. Otherwise, it just turns into raw, unusable heat. That's the difference between the energy conversation and this whole work energy principle. Is now we're going to start looking, I say now, Friday, we're going to start looking at problems where you look at the amount of energy that is in a system and the amount of work done to or by the system, and look at the change in energy and equate that with dissipated forces. Anything non-conservative. You are dissipated forces. You're non-conservative forces. You're not really dissipated, but you are non-conservative forces. And that's the last point I want to make before I let y'all go. Dissipated forces are non-conservative forces, but not all non-conservative forces are dissipated. Okay? I shouldn't have said you were dissipated forces, because you can be, but usually you're not. Usually you're the one adding energy to the system. So you're doing work on the box and then putting energy into the system and doing work that way. And now we're going to start looking at keeping track of all of that work that's done and where does it go. You've seen the demonstration that the guy holds the bowling ball on the pendulum, holds it right up to his chin, lets it go, it swings away, it comes back, and he doesn't move, and it doesn't hit him because it doesn't quite get back to where it started from. Why doesn't it ever get back to actually hit him in the chin? Because that string, that rope that it's hanging from, is not massless. And that pulley that it's hanging from, where it's swinging, is not frictionless. And so all of its potential energy gets converted to velocity at the bottom, gets converted back into potential energy over here. It gets converted back into kinetic energy down here, and gets converted back into potential energy up here. But in the meantime, a little bit of that energy's been lost to friction. And so it doesn't quite get back where it started from. And eventually it'll just be hanging straight down. Of course, if it's a well-designed pendulum, that can take a very long time to happen. That's what we're going to start next. We'll look at dissipative forces and non-conservative forces in the, as we saw, energy conservation.